We're moving into section 4 now, 4.1, polynomial functions and models. So hey guys, this is probably going to be a two-part lesson because this is pretty heavy and there's a lot here. But some objectives here that we're looking at getting to the bottom of by the end of this is identifying polynomial functions and their degrees, graphing those functions using transformations, identifying the zeros of a polynomial function and their multiplicities, and then analyzing the graph of a polynomial function, and then we're going to end with building cubic models from data. Alright, so a lot to get to. Let's try to, at least in this video, I'm going to try to get through the first 2 or 3 objectives. So here we go. Objective 1, identifying polynomial functions and their degree. Okay, so to identify a polynomial function, polynomial functions, if they're in one variable, meaning like they just have x's in them, they're in this form. This form looks to be very confusing if you look at this, but essentially all it's saying is put it in the order of degree. Put it in the order of degree. So what does that mean? That means that the coefficients out front should match the powers that, the order of the powers. So for instance, if I have something like negative 2x squared plus 4x to the fourth plus, let's just say 7x to the fifth minus 1x to the third. If I'm going to put this into standard form, what I want to do is I want to move it around so that the highest degree term is first. So that would be like this, 7x to the fifth plus 4x to the fourth minus 1x to the third minus 2x squared. Okay, so it's in order of degree. The degree is the important thing. And then the number out in front, this number out in front is called the leading coefficient. N, which is just this power here, is known as the degree, as I've already said. And the domain of all of these is the set of all real numbers. Okay, so the domains, the graphs will always go on to infinity in both directions in the x direction, because you can plug whatever you want in for x in these things. Okay, so definition 2. Each monomial that makes up a polynomial is called a term. All right, so here terms are always separated by plus and minus signs. So we have this as a term, negative 2x squared. We have positive 4x to the fourth as a term, 7x to the fifth, and then negative 1x to the third, or just negative x to the third. Those are all known as individual terms, okay? The leading term is always the one with the highest power. So the leading term is the one with the highest power, as I've said. And then a sub 0, where we don't have any x attached to it, that's known as the constant term. Okay, that will always be your intercept, because when you plug in zeros for x, you know, the number that doesn't have an x attached to it, so like say you have like a plus, if you have like x to the third plus x squared minus x plus 3, we know that if we plug a 0 in for all these x's, okay, plug a 0 in, x-axis, plug a 0 in, I'll be at 3. That'll give me my intercept. Okay, so that's called the constant term. And then if all the coefficients are 0, the polynomial is called a zero polynomial, which has no degree. Okay, which is interesting, but we're not really going to worry about that too much because those are no fun. But polynomials are usually written in standard form beginning with the non-zero term of highest degree, as I've always said, highest degree, and continuing with terms in descending order according to their degree. So always put it in order of degree. If a power of x is missing, it is because the coefficient is 0. All right, that is also an important point. So if I have like x to the fifth plus x to the third, what that means is I also have an x to the fourth, but it's 0, so I don't include it. All right, that's important to note, though, is that there is that missing power in there. It's just 0, because when we go to find, when we do some long division later with these things, we're going to need to put in a 0 in there as a placeholder. All right, so kind of important just to note right now. So example 1 says identifying polynomial functions. So for a polynomial to be a function, I want to just make this very clear. We need to have non-negative degrees, non-negative powers or degrees, and then they need to be integers. And we remember that if we have something like the square root of x, I don't know if you guys remember this, but this is the same thing as x to the 1/2 power. Therefore, anything that has a radical is not going to be a polynomial function because it does not have an integer or a whole number power. Okay, so let's take a look here. Looking at this first one, what I want to see is, are all of the powers positive? And then are they all whole integers? And what I see is, yes, this is like x to the first, that's a whole integer. This is x to the fifth. Those powers, if you will, are positive. So this would be, yes, this is a polynomial. However, for our second guy here, this is like saying, this is the exact same thing as like saying x plus 4 to the 1/2. And in that case, the power here is a fraction, therefore this is not a polynomial function. So we would say no. All right. Then it says to write each in standard form and identify the leading coefficient. Okay, so maybe I should do that for this one. If I'm going to write this one in standard form, it's going to be negative 2x to the fifth, right? Because this is my highest power, this term, plus 3x, because that's my next lowest term, minus 1. Constant will always come last, so I can say f of x is equal to this. That's the standard form. The leading coefficient in this case, the leading coefficient, if they ask you what that is the number out in front when it's in standard form. So the leading coefficient is negative 2, and the constant term, we'll call it the CT, is negative 1, because that's the one that has no variable attached to it. Okay. So continuing on here, let's just run through some more properties. Properties of the summary of the properties of the graphs of polynomial functions. So if we have no degree, it's the zero function, which we've already mentioned. We won't see a lot of that. But if f(x) equals 0, it's just 0. So that's pretty straightforward. If the degree is 0, we're on the constant function. So if we have a degree 0, think about this. Anything to the 0th power is just 1, right? So if I have like 2x to the 0, that's essentially 1, so that's equal to 2. They will never write it like this in your textbook or anything, but know that that would be just a constant whenever you have something power to a 0. Okay, and then the linear function is just meaning that there's the highest power is 1. Then the quadratic function, a specific function in which the highest power is 2. Okay. Property 2, the graph of every polynomial function, this is important, you guys, is both smooth and continuous. Okay, so by smooth and continuous, we mean no sharp corners. No sharp corners. And by continuous, we mean the graph has no gaps. All right, so you can draw it without lifting your pencil. For instance, this would be an example, right? You can draw this graph right here without lifting your pen. For this other one, I cannot do that, right? There's a corner here, there's a cusp, but then we stop, and then there's a gap, so I have to lift my pencil, I have to cross over that hole. So when you have to lift your pencil, then you know it's not a polynomial function because it's not smooth and continuous. All right, so I always tell students, like, if you have to lift your pencil to do it, you're not on a polynomial function. Okay, definition 3. A power function of degree n is a monomial function of the form a times x to the n, where a is a real number, a cannot equal 0. Okay, so this is just a power function that just says, that each monomial that makes up a polynomial is basically just defining what that is. Okay, so we can't say that a is 0. If a is 0, then this whole thing goes away. Like if we have 0x to the third, then it's just nothing, right? So a can't equal 0. And n has to be bigger than 0 if we're in a power function. Okay, so we have to have a power greater than 0 for that for that x to remain inside of that polynomial function. So if you have x to the 0 again, that's equal to 1. Right? Anything to the 0th power is equal to 1. Therefore, it's not a power function of a degree n. Okay, so graph some power functions on Desmos. So this would be very important for you guys to try out. We'll do some of these in class. But you'll notice that when you do this, your even powers are going to act a certain way, and your odd powers are going to act another way. And what I want you to focus on when you do this is the end behaviors. Okay, with every even function, what you're going to notice is with an even function, the end behavior is going to stay the same. So if I start a graph like this, okay, no matter what it does in here, if it's even, it will end in the same direction that it came from. We see that with y equals x squared, right? Okay, so take a look at those if you don't believe me. Look at some pictures of these. For the odd functions, however, if you had like y equals x, we start in one direction and we end in the other. The same is true for x to the third, x to the fifth. Any odd power will start in one direction, end in the other. If it's positive, it'll go up from left to right, and if it's negative, like negative x, it'll go down from left to right. So if I have like a negative 2x to the third as my leading coefficient, then I know the whole graph is going to act like that, where I start in the positive and go to the negative. Maybe it does something in between, but in general, that's what it's going to look like. Okay, so the odd powers versus the even powers. It's important to note the end behaviors with those and keep those in the back of your mind. Okay, so property 3, properties of power functions. Okay, f is an even function. If f is an even function, so we're looking at evens, okay, then we know that it's symmetric with respect to the y-axis, meaning the end behavior is going to be the same. The domain is a set of all reals. The range is a set of non-negative real numbers. That's just for a power function. It can go into the negative, so don't. This is just for a base power function. Okay, the graph will always contain the points negative 1, 1, 0, 0, 1, 1. As the exponent n increases in magnitude, the graph is steeper when x is less than negative 1 or x is greater than 1, but for x near the origin, the graph tends to flatten out and lie close to this is when we don't modify it at all. Okay, guys, so if you're graphing like x squared, x to the fourth, x to the sixth, all of these powers hold true. Obviously, we can modify them, right? So if we modify these at all and put them in the context of a bigger polynomial, then these rules don't necessarily hold up, but they just become transformed. So we use transformations to move these rules. All right, so these rules I don't like focusing a lot of energy on, but because we can look at it in the picture and kind of see what happens with these. Okay, the odd functions, again, they're symmetric with respect to the origin only if we're looking at an individual power function, but the bigger idea is they go off in different directions on the end behaviors. The domain and range are always the set of all real numbers, okay, because you can plug in any x and you'll get a y value out, and it's going on to positive infinity or negative infinity in the y direction because it's going in opposite directions. The graph will also contain these points for the power function, but again, those could be modified, and it flattens out in the same areas as an even. So objective 2 says to graph polynomial functions using transformations. Okay, so we're going to graph this function using a transformation. If you have this as the graph, it's important to put it in standard form first. So it's helpful to rewrite it in standard form where we have negative x to the fifth plus 1. Okay, what we know about this is since it's an odd power, it's going to start in one direction, go in another, and since it's negative, we know it's going to start in the positive direction. It's going to do something, it's going to cross at 1, and then it's going to go off into the negative direction. Okay, so if these are your options here for what this thing looks like, then we know, since it crosses at 1, we know that this has to be the correct answer if they give you like a multiple choice type question. If they don't, what you need to do is plug some values in, so we can always make a table, right? An XY table. You could plug a 0 in, you know you'll be at 1. You could plug a 1 in, and 1 to the fifth is just 1, but then that's negative, right? So if you plug a 1 in, you'd be at negative 1 plus 1, which is 0. Okay, so that lines up. And then if you plug a negative 1 in, negative 1 to the fifth is negative 1, negative 1 times, negative negative 1 is positive 1, 1 plus 1 is 2. So at 1 you're at 2. Okay, so it's got to be this graph here. Okay, so you can always make an XY table. You can use Desmos if you need to, but I don't want you guys to crutch on that for this chapter particularly. But then example 3 says graphing a polynomial function using a transformation. Okay, so we want to look at the base function here, right? So the base function is going to be x to the 6th. All right, so we know that this thing is even, so it's going, you know, in the same directions where it's in behavior, right? What else do we know? We know that if we did have x to the 6th, that it would go through the origin, but we're modifying it somehow. Okay, so since we're modifying it by, like, inside the function, we're shifting it plus 1. So what makes that go to 0 is a negative 1, so we're shifting it to the left by 1. Okay, so instead of it being at 0 here, we're going to shift it to the left 1. So it's got to be this guy right here. Okay, and you'll see that with all these even functions that they just kind of flatten out here, and then they go on to infinity in the same direction. Okay. Objective 3, identifying the real zeros of a polynomial function and their multiplicities. Okay, so let's get some definitions in here, you guys. This will be the last thing we do on this video. It says if f is a function and r is a real number for which f of r is 0, then r is called a real zero of the function f. As a consequence of this definition, the following statements are equivalent. R is a real zero of a polynomial function, if we're going to define it with r's. Okay, r is an x-intercept. R is x minus r is a factor. Remember that factors are places where we cross zeros. And r is a real solution. So we learned this in Algebra 1, right? That a place where it crosses x is known as a zero. It's known as an x-intercept. It's known as a solution. And we also know from Algebra 1 and Algebra 2 that if we factor something, at x minus that r will always give me a 0, like where it's crossing, right? These places here, we found those with factors in those classes. Okay, so example 4 says finding a polynomial function from its zeros. Here it says find a polynomial function of degree 4 whose zeros are negative 1, negative 2, 2, and 4. So if these are the zeros, you guys, what they're asking you to do is they're saying, okay, if those are the zeros, then I know the factors for those things. Okay, if it's negative 1 is a 0, then x minus negative 1 or x plus 1 is a factor. X plus 2 is a factor, because it's negative 2 would make that go to 0. And then x minus 2 is a factor. And also x plus, minus 4 is a factor. Okay, so if you plug any of those zeros in, you get that guy. All right, they want you to find the polynomial, though. So they want you to actually FOIL these out and get the polynomials. So a little refresher on FOIL. First, so what I'm going to do is I'm going to actually FOIL these two first, then I'll FOIL these two, and then we'll combine them. So we have x times x, which is x squared. X times 2, which is positive 2x, right? And then 1 times x, which is just x, and then 1 times 2, which is plus 2. All right. So we have that guy. And then we want to multiply this guy by the product of this one. All right, this could be simplified, by the way, to x squared plus 3x plus 2. Okay, now let's do this one. X times x is x squared. X times negative 4 is negative 4x. Negative 2 times x is negative 2x. And then plus 8. This can be simplified to x squared minus 6x plus 8. So now I've got it down to 2 terms, and what I want to do is I want to FOIL it again. Okay, so I'm going to go this times this, this times this, this times this. And clearly I'm going to need some more room, so I'm going to just kind of cruise up this direction here. So hopefully you jotted that down. If not, you can rewind the video. Okay, so when I do that, x squared times x squared is x to the 4th. Remember that when you multiply those together, you add the powers. Okay, add the exponents. Okay, then x squared times negative 6x would be negative 6x to the 3rd. And then x squared times 8 would be plus 8x squared. Okay, so I'm done with this term. Go on to the next one. So then I'm going to take 3x times x squared, which would be plus 3x to the third. Okay, and then 3x times negative 6x is negative 18x squared. 3x times 8 would be plus 24x. So again, what am I doing? I'm taking the middle term and I'm distributing it to all three pieces. Now we're going to go to the last term, so I'll do this one in black. So 2 times x squared would be, so we're just going to continue down here, plus 2x squared. 2 times negative 6x would be minus 12x. 2 times 8 would be plus 16. Alright, assuming I didn't make any multiplication mistakes, now I can combine like terms, and then I'll have my polynomial, which is a little bit of work, but let's try it. So for the fourth power, that's the only one we have, so we have x to the fourth. Notice there was 4 zeros there. Okay, then for the third power, we have this guy and this guy, so negative 6 plus 3 gives me negative 3x to the third. Okay, so that takes care of this, this. Now I got to go to my 2's. Notice now that we have three squared terms. So let's highlight those. We got this guy, we got this guy, we got this guy. So if I add those guys together, 8 minus 18 gives me negative 10 plus 2 gives me negative 8. So negative 8x squared. And then we're done with those. Then we're going to combine our x terms. 24 minus 12 is positive 12x plus 16. Okay, assuming that we did all of our multiplication correctly, that is the polynomial that would give me those 4 zeros. Okay, so if you graph this on a graphing utility or on Desmos, you should see that it gives you those 4 zeros. And let's see, did we get that correct? X to the fourth minus 3x to the third minus 8x squared plus 12x plus 16. I believe we nailed it. Cool. And the graph looks like this when you guys get it onto Desmos or onto your graphers. Okay. Those are the zeros. Using the zeros to come up with a polynomial. Definition 5. If we have x minus r to the m, if x minus r to the m is a factor of a polynomial f and x minus r to the m plus 1 is not a factor, then r is called a zero of multiplicity m of f. All right, what does that mean? Let's take a look here. So this is, we'll do example 5, 6, 5 and 6, and then I think we'll be done. I'm wondering if I should I think what I'll do, you guys, is I'm going to pick up right there next time. So we'll end this video right here.